Right now I'm presenting to you Physics 2211 Lab 5, and I chose the falling slinky, which is this video right here. Boom. Okay. So, quick table of contents, what we're going to be getting into an introduction, followed by some observations and a computational model before the final comparison and conclusion. So the purpose of this lab was to observe the motion of a falling slinky, explain and analyze it using Newton's law of motion. And the fundamental concepts here, Newton's first law of motion, that an object remains at rest or in motion at constant speed unless acted on by an unbalanced force. And some important equations to keep in mind here are the position update formula and the velocity update formula, as well as that velocity is the change in position over the change in time. And finally, gravity, which since we're close to the surface of Earth can be simplified to force of gravity equals mg. These are the primary formulas I'll be using to derive information from the tracker software and to create like an accurate glow script model. But another important concept I used here was just the general concept of tension or drag force. So my observations in the tracker model, first I'm going to start with the system and surroundings, which I define to be the system including the Earth and the slinky and nothing in the surroundings so that all energy stayed within the system. And this is just a screen cap from my tracker input. What I did for this video is I took that clip that I showed at the beginning of the slideshow and I used the tracker software to track its position at each time. And from that, I got a graph for the x coordinate and for the y coordinate. So the initial conditions that I observed from this tracker software were that my initial position is 0, 0, as well as my initial y velocity being 0, 0. Since we're looking really just in the j-hat direction, I only really took account for the y direction velocity. And though the slinky starts with no motion, the motion is measured from the bottom of the slinky, and the slinky doesn't begin falling until the slinky has fully collapsed. And this whole video takes time this whole falling motion takes time over 0.4 seconds. So here I'm gonna evaluate the computational model that I created from GlowScript. These are the conditions that I put in. Here shows the initial conditions, which is again that 0 vector, and a mass that I found online for a standard slinky to be 0.2 kilograms. On the right-hand side here shows like the while loops that I use to kind of simulate the motion, which for the top section, while the slinky is not moving, basically cancels out. F net equals ball times mg j hat minus ball times g j hat, which is 0 to show constant motion. And then for the rest of the falling, it is not that. Here's the final graphs that I got from both. This glow script model here in green, it kind of just shows more towards the end of the motion. It doesn't show the kind of plateau that we have in the beginning because I really only simulated the end piece there, and they are fairly similar. I kind of attribute all the differences to kind of errors with using the tracker software. Why does it matter? The fact that the slinky has 2 different stages of motion according to how it was compressed shows how the presence of other forces affect the acceleration. Before, the forces of the slinky were unbalanced, the forces of the slinky were balanced due to tension up higher in the slinky holding up the bottom, and the bottom began moving once it was compressed. And how this showed up visually was the slinky being virtually still in the beginning before it dropped in the end. And that concludes my presentation. Thank you.